Okay, so topic of my talk today is on effective causal learning. Okay, the usual problem with causality is summarized by this diagram, right? As we always know that correlation doesn't mean causality because there could be an underlying cause. So a typical example is smoking causes cancer. So that you see a lot of correlation between smoking and cancer. And the tobacco company may argue that we have a gene for both smoking and cancer, and so you can't establish a causality. But what I mean by effective causality is something like this. So if you are looking for a mate, right, it doesn't really matter whether this is there. All you know is that if someone smokes and he or she might get cancer later in life, and you may not want to be with the person, or you may want to have other things. So the idea comes from Lee Smolin, who said that all physical theories are effective in the sense that they're only true with respect to some truncated portion of nature. So like even these time-driven laws may not always be true, but they're effective, right? We use them for as long as we can until new laws are discovered. So I will show you another more concrete example. In this case, there is this person holding a remote control, trying to control the car. Now, even if this person is a person from the wild who has no idea about remote control, electromagnetic field, and so on, when he moves the joystick, the car's wheels move in a certain way. So the correlation is actually, or rather the causality is actually very easily established, right? After playing with the joystick a few times, you know how to control the wheel. Sorry. Now, but if you move the car to a distance, right, and then try to use a smoke to indicate the movement, and then you try to do the control. And to learn this causality is going to be much more difficult because of all the wind and compounding factors and so on. So this is what I believe where statistical causal recovery comes in, right? We use a lot of statistics to establish this. But if you see this thing right in front of you, and you can see that any movement here causes some movement here, this is what I call effective proximal cause recovery. You can establish a causality very easily. So the idea is that if I push this, or I push some object, it moves right away. That's a causality. And you can still, of course, argue. Earlier on, I should go back. Yeah, okay. So this is the movement of your hand and the movement of an object that you push. Now, if you want to be strict about this, you can say that, well, perhaps it's God that causes me to move my hand and causes the object to move, right? You never know. It goes back to this situation here, right? Movement of my hand, movement of the object, God, right? So, but I don't think we think about God all the time when we deal with things in our environment. We assume there's a causality and we learn that. And if you have wind that happens to come by when you are moving this thing, right? Try one more time, right? There's no wind and it still moves, so you don't need the wind to move the object. So effective proximal cause recovery can be very, very rapid. Now, there's another factor involved. The earlier causality, I call it diachronic causality. That means it's time. An event happens at one moment in time followed by another event. This is what I call synchronic causality. So for example, if you push an object, it moves. The first time you did that, you might think that you need to do it in a room because the context might be the enabling factor. But if you move this outdoor, some other places, and the same thing happens, you relax this condition, right? So you sort of establish a more general rule that says that as long as I apply a force, it doesn't matter what the background is. Now, of course, this removal of this cause may be brought back in a different situation. Suppose you go to outer space and now you find that this force law doesn't work anymore, right? So what you need to do is you have to bring back the previous conditions, right? So that means, in this case, your assumption that this is not necessary is wrong, right? Perhaps this background and this background both participate in what I call disjunctive synchronic cause, like this. So if you have done this all over the world, I mean on Earth, and in space it doesn't work, then these are the preconditions for this model. Okay, so to make it more abstract, I have created this little environment with three events. Event 1 that happens, maybe we can say an object appearing in location 1, object 1, 2 appearing in location 2, and object 1, 3 appearing in location 3 at this time frame, right? So you can see that there's this appearance follows by this appearance, right? This appearance followed by this appearance. So there's a consistent temporal relationship. So we can create a causal loop between event L2, 1, 2, and 1, 3. But not this, because there's no temporal correlation. But L1 is always there. So L1 could be a synchronic cause. So a background that enables the L2, L3 relationship. Now, suppose L1 is not always there, right? L4 appears. So this is a similar situation to the earlier one I mentioned. So in this case, we can say that, well, L1 and L4 are not the necessary synchronic causes. Now, unless later on, somewhere here, right, further downstream, the relationship between L2 and L3 no longer takes place when L4 or L1 are not there. So that means you've got to restore L1 and L4. And so L1 and L4 are the kind of disjunctive synchronic cause for the event L2 and L3. Okay, I'm going to apply this to a concrete problem, and I'm going back to a very basic issue in AI, which is a search issue, right? So this is a spatial movement to a goal problem. So you start from a position and you need to go to the goal, right? And you can move a lot, you can make a lot of elemental move. And the standard way to do search would be to start from this position, try all directions, right? 360 degrees and so on, right? Now if you do that blindly, it's incredibly combinatorial. You can also build in a domain-specific knowledge that says that, right? To reach the goal, I just keep heading toward the goal. But that is too contrived. So is there a middle point somewhere? Or a general algorithm that is no domain, that is non-domain specific? Yes, the usual A-star algorithm is non-domain specific, right? But typically, uses a heuristic, which is the minimum distance to go. But that cuts down the search, right? But you still need to, firstly, you still need to expand 360 nodes at each level. At the first level, and also at all the levels, all the way down the goal, right? And not only that, if you change the position, start and goal, you have to redo everything. So there's no generalization. Now, can we use the causal algorithm that I mentioned earlier to do a better job? Okay, I'm redrawing the start and goal, and now I'm putting in some parameters, right? Like in this case, this is the absolute angle A3 relative to the entire frame. This is the relative angle, to the goal. This is the absolute location, and this is the there's a relative distance there, and then there's absolute location. And assuming that these parameters are obtainable through some kind of visual system. So the first thing you do is, at this starting point, you don't know where you should go, so you try all the positions, 360 positions. And I'm just looking at 4 of the nodes here, right? Node 1, node 2, node 3, node 4. And what you're seeing is this. Suppose you apply a force to the location 2, right? You create a causal link here. And this will be the diachronic relationship. This is the synchronic conditions. That means this event, this causality takes place at this location, these parameters, and so on. Now, when you apply the closest distance heuristics, you pick this goal, right? And this node to be the best direction to move. So it turns out, moving toward the goal is a good choice. Now, so what we're trying to discover is what are the synchronic enabling conditions that causes the minimum distance to go, right? How do we find the rule that causes us to always go toward the goal. So in this case, right, because all these conditions are very specific, so we put down all the conditions. Now, if you take this one, do another expansion, right? Next level, you start from L4, and this is picked as the minimum distance to go synchronic condition. So now you can relax this because L1 and L4 are not the same. But at A3, A0, and the location of the goal stay, right? Now, at this point, you don't need to search any further because what it says here is that all you need to do is keep going in this direction A3 and you reach the goal. Right? Now suppose you repeat this whole thing from a different start and goal position with a different absolute angle, what you get will be you relax this further. Right? And you got this most general rule that says that basically it says no matter where you are, starting from where you are in the search path, just keep heading to the goal. Use a zero direction. Right. So this domain-specific heuristic is discovered from a general search process enhanced by causal learning with a non-domain specific heuristic. So basically, after a total of 4 node expansions, you don't need to do any more search. You obviate all future searches. Okay, so just a quick one to apply to a more complex problem, but I don't have time to go to the detail. Basically, this is a crawling robot problem, the robot with two arms that if the arms are moved in a certain way, it will go forward, right? The problem is how to get the robot to go forward. And you can write all these rules to specify what happens in a certain condition. Let's say when this is touching and when beta is angle greater than 0, when you decrease beta, it will move forward, right? That's when this is touching. When it's not touching, then when you decrease beta, it doesn't move forward, and so on. Now, this can also be discovered using our causal learning method. Basically, these are just a synchronic conditions. You get data from the tactile or your proprioceptive input, and you establish what condition when you do certain things happen. When you did something else, something happen. If you get this type of rule, you can do a backward chaining, and you solve the problem. Right? Now, how does this compare with other methods? In traditional AI, normally we write these rules ourselves. We use our own human, observation, and we write these rules down. And of course, there's no learning. But if you have written all these rules, the problem solving is pretty fast. For reinforcement learning, the problem solving process tends to be much longer. So what we have here is best of both worlds. First, we learn these things. There's no built-in rules. And secondly, having these rules, the problem solving can be very good. So we have applied this to a StarCraft game environment where the agent is supposed to find a rule to attack another agent. And there's specific rules that is built into this environment that allows this to happen. And there's a lot of parameters involved. After 2 trials, the system is able to identify the necessary condition, and it knows how to attack from any position. So the method works. So in summary, search and exploration combined with effective causal learning allows general causal rules to be rapidly discovered, and also the subsequent searches are drastically reduced or obviated. Thank you.